Good morning. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 23, on change of phase. This will be a pretty short lecture because there isn't a whole lot in this. So basically, as you know, temperature correlates to the average kinetic energy of the particles. What I'm calling thermal energy, average energy of the particles of the substance. So what I'm calling molecular energy, thermal energy, internal energy, heat energy, we call it all those things. Temperature correlates to this. And so we know that we've got solids, I wrote that too big, solids going to liquids to gases. And we know that as you increase the temperature of a solid, increasing the temperature, it becomes a liquid. And then when you increase the temperature again, it becomes a gas. And then with this, we call this melting. When we increase that, we pump in the heat, it becomes a liquid. We call this melting. We pump in the heat, it becomes a gas. We call this like boiling off or evaporating. I'm sorry, my brain's needing to wake up a little here. Boiling off, evaporating, you know what I mean, going from the gas state, from the liquid state to the gas state. And as we pump the heat into it, it breaks down the crystal structure. It breaks down the crystal structure into here, and then it boils off and becomes gas over there. And you sometimes have solids going straight to the gas state. This is called sublimation. You don't see it a whole lot, but it's like that's why ice cubes, if you leave them in the freezer forever and ever, they will eventually shrink. That's sublimation, but we're not going to talk about that too much. But anyway, so as you crank in the heat, as you put in the energy, as you crank up the heat, and you put in more and more heat energy, you will go from a solid to a gas. Now, this is why, actually this is pretty cool. So out here in the desert, they would use olas, I think is what they used to call it, and they have these like clay, the Indians, Native Americans, they would have these, they were really smart. They would make these like clay jars, and usually clay is a little bit like lets a little bit of the water out. What's the word? Water can soak through a little, so usually they glaze them so that you don't lose any liquid that you've got in your jar. You don't want your jar to sit on the table and ooze out in a little puddle. But it's slightly porous, that's what I'm looking for. But what they would do is in the summertime, they would use these olas, these clay jars that were not glazed, so they were a little porous. And they would hang them from the tree branches. So they'd hang this from the, it's super hot outside, 100 degrees, 110, and they'd hang it from a tree branch in the shade. And so, it's got some wind touching it. And as the ola would seep a little bit of water on the outside of it, the wind would come and evaporate that away. And as it's evaporating that away, it's taking some heat with it, remember? Because to go from liquid to a gas, to evaporate that water on the outside.
Is this like a mister?
It has to eat some heat.
Is this like a mister?
Yeah, that's why misters cool you off. So it has to eat some of that heat. And so what's happening is you have that lukewarm jar hanging in the shade, and it's evaporating a little bit. It's true, okay, you're losing a little bit of your water, but when you pick it up to drink it, it's cold. Because that evaporation had to take heat. It needed to take heat, go from liquid to a gas, so it sucks some of the heat out. This is the same reason why hot, warm day, you're in the pool, you get out of the pool, and you are freezing. Because the wind is evaporating. When you get out, the wind, even if it's hot air, is evaporating that liquid that's sticking to your skin. And as it's evaporating away, it's taking heat with it. Because remember, to go from a liquid to a gas, it needs to take in heat. So as it's evaporating, it's taking that heat with it. And that's why you cool off. That's how your body cools you off, it's sweat. Because going from a liquid to a gas will take heat. Okay, so the sweating is your body's way of cooling you off in hot temperatures. Olas is like making it sweat, so it's cooler. Now, the opposite direction we'll see is as you cool things down, as the energy is taken out of the system. So here we've got solid. This is where you're pumping heat, you're pumping energy in. As you put energy in, it goes from solid liquid to a gas. Okay? And now we're going to take energy out. So think you put your thing in the freezer, the cold freezer's reaching a thermal equilibrium, sucking that heat energy out of your object. And that, as you cool it down, it condenses from a gas into a liquid, and you keep cooling it down, and it will finally crystallize into a solid. So remember that when something goes from a gas to a liquid, it's giving up energy. it's condensing. This is why steam burns hurt so much. The hot steam hits your skin, condenses onto your skin, that all that energy to go from here to here is dissipating into your body, which feels terrible. Okay, so you see it as you pump the energy in, things go this way, and as the energy is sucked out, it goes this way when you put your water or whatnot in the freezer. Okay. So here we've got energy in, energy out. As energy is absorbed or energy is taken out, released, energy released. This is how a refrigerator works. So a refrigerator kind of forces the issue, but it's got coolant, it's got like a coolant pipe. There's a really nice illustration right here of how a refrigerator works. It's got a nice look here. So if you can see here, what your refrigerator is doing is you've actually got like a compressor pump that vaporizes the stuff. So as it's vaporizing, it's taking a liquid and it's basically forcing it to become a gas. And then as it's doing that, then it has to take heat in. Then it goes around to the back of your fridge with the condenser coils, and then as it condenses, then it's letting heat out the back of your fridge. That's why the back of your fridge is so hot. The back or the sides, wherever the condenser coils is so hot. So what your pump, what your electrical motor or whatever is doing is it's forcing the stuff, the liquid, to become a gas, and that soaks in the heat from the vegetables and whatnot in your fridge. And then it squirts the stuff to the back, to the condenser coils, and then as that condenses, then it emits the heat there. And then the pump pulls it back around and squirts it back into a vapor, and then it has to do the whole thing over and over again. That is why a refrigerator needs an outside energy source. It needs that outside energy source, that motor, to keep pushing and forcing those phase changes so it can be essentially sucking the heat out from the inside of your fridge and taking it, releasing it on the outside of your fridge. Okay, that was that chapter. There wasn't a whole lot in that chapter. Oh, just remembering you'll see what we talked about when the energy gets pumped in. Here you see that as something is melting, it stays the same temperature because all the extra heat energy is being used up to break up the crystal structure. And then, it gets here, and now all that heat energy is being used to vaporize your water into steam. So it has to get all the way here before the temperature will start climbing again. Because essentially that heat energy is being pumped into breaking up the different phase changes here. Here it's breaking up the crystal structure. Here it is vaporizing, turning the liquid to a gas. So anyway, that was pretty cool with a very practical application of your refrigerator.